Hello viewers, welcome back to the course on matrix computation and its application. So, today we are going to discuss some more facts about the linearly dependent or independent sets. So, let us start with this one. So, this is the lecture number 11. So, this is the another fact we are going to discuss, or maybe it is a theorem, that in a vector space V, suppose we have n number of vectors and that is given to us in the ordered set. Ordered set means they are given in the order. So, V1 is definitely coming before V2 and V2 is coming before V3. So, we cannot change the order of this set. So, this is a set of vectors with V1 is non-zero. Then the set is linearly dependent if and only if one of the vector, say Vk. So, one of the vector coming from these sets belongs to the span of the vectors V1, V2 up to Vk minus 1. It means in this case the vector Vk is coming and that is the linear combination of the previous vector V1, V2 up to Vk minus 1. So, that is the we are going to discuss. And what is the use of this theorem is that suppose I have somebody gives me a set of vectors, a large number of vectors V1, V2, Vn and ask me to check whether it is going to be linearly independent or dependent. Then we have to take the linear combination, and in that case it is becomes very difficult when the number of vectors are large to check whether they are linearly independent or dependent. Like we have seen in the previous examples also, where we have a 5 number of vectors, and in that case we got the matrix that is 4 cross 5. So, it becomes very difficult because we have to convert that matrix into the echelon form and then only we are able to check. So, if I have a 5 cross 5 matrix or maybe 10 cross 10 matrix, then it is very difficult to check whether the set is going to be linearly independent or dependent. Then we can use this theorem. So, in this theorem we take the vectors, and one thing is there that V1 is not 0. So, starting with this one, and that is non-zero, because if it is coming 0, then itself we have the theorem that if one of the vector is 0, then it is going to be the linearly dependent. So, we are starting with V1 is that is coming non-zero, and then we say that the set is linearly dependent if one of the vector, say Vk, is a linear combination of the previous vectors. So, this is a theorem, and let us discuss its proof. So, let us take the case 1. So, the case 1 is that let Vk belongs to the span of V1, V2 up to Vk minus 1. So, that is given to us. So, I am taking this. Now, from here it implies that I can write my Vk as some A1 V1, A2 V2 up to Ak minus 1 Vk minus 1 for all the scalars A1, A2 up to Ak minus 1 belongs to the field. And from here I can write, now this one can be written as, I can write as minus Vk plus A1 V1 up to Ak minus 1 Vk minus 1, that is equal to 0. So, this one we can write, and from here you can see that this value of A1, A2 up to Ak, it can be any value, but the coefficient here is always minus 1. So, from here I can say that since coefficient of Vk is minus 1, which implies that the set of vectors V1, V2, Vk minus 1 and Vk So, this set of vectors are linearly dependent. So, this is the vectors are linearly dependent, and that is what we wanted to show, that if this is there, then the set is linearly dependent. So, one part is okay. So, I take the converse of this one, the second part. Now, let we take, so let I assume that the set S is LD. So, let I take the set S n V1, V2 up to Vn. So, this is a set I am taking of n vectors, and suppose this is LD. So, the set is LD. Set is LD means the vector belongs to these are LD, linearly dependent. So, let this set is a linearly dependent set. Now, so now I want to show you that if we get a vectors, linearly dependent vectors, then one can be written as a linear combination of the previous one. Okay, so, this is what we want to show. So, let we take the vectors S1. So, let us take set of vectors as I just to choose S1 as containing only one element, S2 contains V1, V2 like this one. So, I keep going with this one. So, I can have as I, this is set of vector V1, V2 up to Vi, and then Sn is the whole V1, V2, V3 up to Vn. So, this is the sets I can define from the set Sn, and I am keeping this in the order. So, that is the most important thing. Now, given V1 is not equal to 0, that is already given to us. So, from here and from the previous example, we can say that S1, which is containing only V1, is linearly independent, because we have seen that if set contains only one element and that is a 0 element, only then it is linearly dependent, otherwise it is going to be always linearly independent. Okay. So, this is linearly independent. The same way I just take S2. So, in the S2 we have V1 and V2. So, now V1 is not 0. So, V1 is not equal to 0. So, that is definitely is there. Now, we have discussed that we have a two elements V1 and V2, and suppose it may be a collinear vectors. So, in this case this is also going to be linearly independent. So, if it is going to be linearly independent, that is okay. If it is going to be linearly dependent, now this is the two cases. So, I just take now, if S2 is linearly independent, then okay, no problem. Then no problem. But if S2 is linearly dependent, so in this case if S2 is linearly dependent, that implies that V2 can be written as some scalar multiple of V1, that we already know, and in fact there will be collinear vectors. So, from here we are done, that we are written the one vector as a linear combination of the remaining one. So, it from here we are done, and we have shown that the vector V2 is a linear combination of the previous vector. So, that was the V1, and this is we are done. Okay. So, these things we are here. So, from here we can say that so after doing this one, I reached that let Sk is a set which is linearly independent. So, that is linearly dependent, we are taking this Sk, and Sk minus 1 is linearly independent. Okay. So, in this case my set is linearly dependent, means the vector belongs to this are linearly dependent. Sk minus 1 is the set which is linearly independent, it means the vector belongs to these are linearly independent. Now, from here, now since Sk is LD, so we can write alpha 1 V1 plus alpha 2 V2 alpha k Vk, that is equal to 0 we have with at least 1 alpha k that is not equal to 0. That is why it is the meaning of linearly dependent. Okay, so, at least 1 alpha k will be there which is non-zero. So, then we can have this condition. Now, so and we are choosing alpha k is not equal to 0. So, from here I just can write this one as 1 alpha I is non-zero. Okay. So, this is there, then we write surely alpha k is not equal to 0. Why? Because if alpha k is 0, then because since V1, V2 up to Vk minus 1 are linearly independent. So, these vectors are linearly independent. So, that is why this alpha k cannot be 0. If alpha k is 0, that is also 0. So, they become linearly independent. So, from here I can write that from here minus alpha k Vk I can write as alpha 1 V1 plus alpha 2 V2 alpha k minus 1 Vk minus 1, and from here I can write my Vk as minus alpha 1 alpha k V1 minus alpha k minus 1 over alpha k Vk minus 1. Okay, and from here we can say that Vk belongs to the span of V1, V2 up to Vk minus 1, and this is what we wanted to prove. Okay, so, the moral of this theorem is that when we have a large number of vectors, then we start with the first vector, then taking first 2 vectors, then first 3 vectors, and keep checking once we reached a linearly dependent set. So, if we hit a set which is linearly dependent, then the whole set will be linearly dependent, otherwise it will be linearly independent. So, after this one, now we can also one corollary that a finite subset, I am taking a finite subset S which contains the vector V1, V2 up to Vn of the vector space V containing a non-zero vectors has a Li subset A such that A span A is equal to span of S. So, this is what we are going to discuss. Okay, so, the condition is that we have a set S. So, this is what I have a set S Vn. So, n number of elements are there, okay, of the vector space V. Now, it contains a non-zero vector, because I am saying that it can be 0 also, V1, V2 up to Vn, it can be 0 also. So, we are saying that contain a non-zero vector. Okay. So, all this containing a non-zero vectors has a Li subset A such that this one. Now, so what we are going to discuss here is that, now let I take a subset A. Okay. So, that subset contains few vectors. So, maybe I just take V1, V2 up to Vn minus 1. Suppose I take these vectors, okay, and A is linearly independent. So, A is linearly independent, that is sure. Okay. So, I am taking one subset of S and which is linearly independent. Now, it says that S, the span of S is equal to the span of A. But how we are going to discuss this one? Now, we know that let I just take the set S is linearly dependent. Suppose the set S is linearly dependent. Okay. So, now from here, or maybe I can, so linearly dependent. So, I can write that and Vn can be written as a linear combination. So, I can write alpha 1 V1 plus alpha 2 V2 alpha n minus 1 Vn minus 1, and suppose this is happening, because suppose this is the vector Vn can be written as a linear combination of the previous one. Now, from here, now the Vn is a linear combination of this one. So, I can remove this vector, because it is already the linear combination of this one. So, then I can remove this, so it remove. Then the remaining vector I have a set, and that set is a V1, V2 up to Vn minus 1. Then obviously, now what I am going to do now, I will let take any x belongs to, suppose I take from span of S. So, let I take the x belongs to the span of S, which implies that x can be written as, and S I am taking just one element less, just for the it is coming from S. So, x can be written as alpha 1 V1 alpha 2 V2 alpha n Vn. So, I can write like this one. So, it is a linear combination of this vector. Now, also Vn is a linear combination of V1, V2, Vn minus 1. So, it is also a linear combination of V1, V2, Vn. So, that can be written as alpha 1 V1 alpha n minus 1 Vn minus 1 plus, now it is the this one, and that is already there, Vn is written as this one. So, I can write from here, maybe I just change the notation, I can write, so let us write this as I just write it as a A1. So, A1 V1 A2 V2 A n Vn. So, this can be written as a1 v1 up to a n minus 1 v n minus 1 plus a n, and v n I have already written. So, it is alpha 1 v 1 alpha n minus 1 v n minus 1, and this one can be written as a 1 plus a n alpha 1 v 1 up to a n minus 1 plus a n alpha n minus 1 v n minus 1. So, it is a scalars again. So, it from here I can say that x belongs to, and this is the linear combination of the vectors belongs to the set S, because the only condition is that the has a Li subset A. So, because A is a Li, so this is written as a Li subset A. So, that we have to keep in mind. Okay. So, from here this become the linear combination of the set the vector belongs to the set A. So, I can say that it means the x belongs to the span of A. Okay. So, I have taken the x from the span of S, and that belongs to this one, which implies that this is a subset of this one. Okay. Similarly, I can take the converse, and using these two, then I can take element. So, and that we already know that I have taken the set A, that is a subset of S. So, definitely the span of A belongs to the span of S. So, that is already true. So, in this case, from here I can write also A is a subset of S. Okay. So, then I can choose element, and A is a Li vector. So, this one I can take, because I can from here I can take that if S is Li, then nothing to prove, because if S is Li and A is a subset of that we have already seen that if from the previous theorems we have seen that if I have the Li set, then its subset is also Li. So, A is a subset of A, then it will be Li. So, nothing to prove. The only thing is that when S is LD. Okay. So, from here I am taking that if S is linearly dependent. So, if S is linearly dependent, then we have taken a subset of S, that is A, which is Li, and then I have proved this one. Now, I just take the converse of that one, and from there so this can be proved with the previous theorem also, in which we have taken this way. So, we can even use this theorem also in proving that one. Now, so after this one we want to define some another term, that is what is going to happen if we have a infinite number of sets, infinite sets. Suppose I have a infinite subsets of vector space V, like we have a vector space of all the polynomials, and in that polynomial suppose I take a set S like this one, which contains 1 x, x square, x cube, x 4, all the powers of x. So, this S is the infinite number containing the infinite number of vectors, belongs to the set of polynomials. So, an infinite subset S of the vector space V is said to be linearly independent if every finite subset of S is Li. So, for example, if I take this one and I want to check whether S is Li or Ld, then what is going to, because ultimately we are not going to take the linear combination of all the infinite number of elements. So, for this one what we are going to do is that we will choose any finite number of vectors belongs to S and then show whether it is Li or Ld. Okay. So, any finite number of sets, you take any finite number of sets, finite number of vectors, show that, suppose it is coming Li, then you can take any other vectors that is also coming Li, only then you can say that this is a Li vector. So, like this one. So, in this case this is a set I am taking. So, I just choose, for example, I choose a set maybe S1 as x square, x cube, x 10 up to 10. Then what I will do? I will take the linear combination alpha 1 x square plus alpha 2 x cube up to, so alpha 9 x 10, I put this equal to 0, and then, so this is the polynomial, 0 polynomial, and from here we will take the coefficients equal, and then we will find out that this alpha is are 0, and from here I can say that alpha 1 up to alpha 2 up to alpha n 9, they are coming 0 in this case. So, this set of vectors are Li. Similarly, we choose any vectors that is suppose coming also Li. So, if from here I can say that this is Li, and then from here I can say that S is linearly independent set. Okay. So, this way we can do when we have a set containing infinite number of vectors. Now, so after this one, I just take one more example. It is a different type of example to check whether the set of vectors are linearly independent or dependent. Okay. So, example, check the set of vectors I am taking. Suppose I take the vector Sx, sin x, sin 2x, sin 3x, sin nx. So, these are the vector I am taking from the vector space V, that is set of all the continuous function from minus pi to pi. Okay. So, I am taking the continuous function from minus pi to pi. So, this is the vector space I am taking, and all these vectors are coming from this one. Okay. So, for example, sin x belongs to C minus pi to pi. So, x is coming from here. So, all these vectors belongs to this one. Now, I want to check this set is Li or Ld. Okay. Now, what is going to happen? So, this is my solution. So, we will take the linear combination. So, let us write the linear combination. So, linear combination will be a1 sin x plus a2 sin 2x up to an sin nx, and that is coming equal to 0 function. So, this is the same way we have done in the previous example, where we had only 3 vectors x, sin x and cos x, but now we have a n number of vectors, and now if I suppose do the same thing again and again, taking the derivatives, then I will get n cross n matrix. Okay. So, maybe I can take the derivative of this one, and I can write here minus a1 cos x plus 2 times a2 cos 2x and an cos nx equal to 0. One time derivative I have taken. Similarly, I can take another derivative, but in that case it is not going to give. So, suppose I am taken sin x, then cos x, then minus sin x, then minus cos x, like this one I can keep going. So, I will get this type of set of equations, and from there we are going to have a matrix that is maybe n cross n. So, in this case I am going to have n number of equations. Okay. So, n number of equations we going to have in this case. Now, the question comes that how we can solve, because if I write this as, so you will see that I will get a matrix of this form a1 a2 up to an, and this is I am going to have 0 0 0, and here I am going to have sin x, sin 2x, sin 3x, or maybe sin nx, then cos x, 2 cos 2x, 3 cos 3x, n cos nx. Okay, then minus sin x, then minus 2 square sin 2x, like this one. So, n time derivatives I am going to take, and this matrix is going to be n cross n, and this is n cross 1 and this is n cross 1. Now, the question is that, because now it is very difficult to take the determinant of this matrix. So, how we can find out the determinant of this, and in this case if I put the value of x equal to 0, then definitely this row becomes 0, and in that case always I will say that the one row is 0. So, the determinant is 0. So, I can say that this is a linearly dependent. Okay. So, these type of problems how to solve, that we are going to discuss. Okay. So, let me stop here today, and so today we have discussed a few more facts about that one, and then we have started with the example in which we have a n number of functions that is coming from the vector space of continuous function from minus pi to pi, and then we check that how we stuck that how we can find out that the given set of vectors are linearly independent or dependent. So, you can think about this one, and we will discuss the solution of this in the next lecture. Thanks for watching. Thanks very much.